Alright, so the chapter of the day is Subnetting, chapter 8, and basically, as said in chat, it'll be the kickoff point for the second assignment, which strangely enough has subnetting in it. So this is why it's been delayed until now. So we'll have a look at IPv4, how we changed the addressing schemes to support variable length subnets, because under classful addressing, which was the first method, every subnet had to be equal and the same. So we'll look at how that's changed the landscape of addressing, and we'll have a quick look at IPv6 addressing assignments as well. So first things first, we need to understand that a broadcast domain is. So within a layer 3 section of the network, we have a broadcast domain. So every interface on a router is a broadcast domain. Okay, so broadcasts cannot be stopped at layer 2. They are only stopped at layer 3. So just be aware of that. And so when we look at IP addresses and their range, we need to understand that the last address in the range is the IP broadcast for that subnet. The way I do the chapters is they're all turned on each week. If you wish to redo it, you just go back in and redo it. Okay. By you reactivating the exam, it wipes out the result and puts the current one in its place. Okay. So the problem with a broadcast domain is the more devices you get in the domain, the slower the network operations become, because switches just propagate the broadcast, because the mechanism for switches is a broadcast packet has to be sent out every interface except for the one that was received on. So we can reduce the broadcast domain by making the network segments smaller. So we basically create more networks that we use, and the broadcast domains become smaller, and the Ethernet protocol can become a little bit more efficient because there's less conflicting broadcasts within the domain. So some of the reasons we subnet is to reduce that overall traffic on that network segment, and it also allows us to control the policies of the network, so security policies, administration policies, and apply them to smaller segments of the network, so we can really target the policy specifically to that area of the network, which makes it a bit more efficient and easier to implement policies. Okay, so just a refresh on the standard classful boundaries and the blue. So we have our class A address there, our B, which is 16. So the first 8 bits in A, first 16 bits in B, and then in class C was 24 bits used. Now, the problem with that is because each network had to be exactly the same size. Even when we subnetted them, we would lose a lot of hosts, because when we do the point-to-point link between two routers, okay, that's dot 1, that's dot 2, we would still lose all the remaining hosts on that subnet. So under classful addressing, we would lose a bucket load of addresses when we divided the network up into subnets. And because of that, we ran out of address spacing very early, and we had to come up with a way of addressing that change. So the standard way of addressing was just to use the octet boundaries very quickly. So on the /16, for every increment of the second octet, it was a brand new network. So you had, from the very first octet of the first, and then the very last address is the broadcast. So that's where the host, geez, my writing today is host bits or ones. Okay, so because it goes across the boundary, got to remember that, because when we're talking binary, we're talking about 32 binary digits, not the octets. So just be aware of that as well. So, all right. So with the introduction of classless subnetting, we were able to change the size of the networks depending on our need. So we can now take any network and break it up into smaller pieces. So in this first example, we would have the 0 and 128 network. Now we would grab one of those networks and break it up into smaller parts. So on the second one there, by borrowing an extra bit from the 128 network, we would then have the 128, and it's now 64-bit increments. So we would have the 192 network there as well. Okay, so if we borrow the 192 network and break it up into smaller parts, again, by taking 2, which is 32, which is 224. So each time we can take any network and borrow another bit and create another set of addresses or networks out of it. Okay, so it's really important when we grab these ones here. Okay, so if we grab the 240 network, we would get the 240, 244, 248, 252, and by this method we can just take one of these networks and do our point-to-point addressing. So it became a lot more efficient to break up the networks into just the sizes that we needed for the number of hosts that we use within that network segment. So just as a recap, I know I've given you lots of binary problems over the weeks, so hopefully you've done them. Just remember, for every bit that you borrow, which is 2 to the power of 1 bits borrowed, so that gives you 2 combinations for each bit, which is exponential. So if I was to borrow 3, 2 to the power of 3 is 8. Okay, so that would be the total number of potential networks I can get. And the same calculations for the number of hosts remaining. So if I borrowed 3 bits, that leaves 5, so 2 to the power of 5. So quick way of doing it, if that's 64, then each one of these has a potential 64 hosts on it, but I can't use the first or the last host address in every network, so I would have 62 usable host addresses within that network. Because the first address is the network address, the last address is the broadcast address for that subnet. Okay, so the magic number, as they say, is the last bit borrowed in the network portion. That's what the network's going to increment in. So it will go up in lots of 64 or 32, 16, 8, whatever that value is. And you can use that to quickly calculate the network addresses and the host addresses. So from that, if we look at the 64 network, so the network address is going to be .64, first host 65, broadcast, and last host. So the broadcast is going to be 1 less than the next network, so that's 95, and 1 less than that is 94. So on the .64 network, that's my usable host range from .65 to .94. Now, once we've got the subnets calculated, we can assign them to the individual hosts. Now, the way we do that is by assigning in these labs, we generally use the first host as the gateway, and then we assign them off. All right, so this is the actual network, not the address of the switch, which we need to assign as well. So it's very poorly positioned in the graphic. It is a question I get asked to clarify quite a bit. So the gateway address is 129. So when we're configuring PC2, we give it the .130, and the subnet mask of /25 is 255.255.255.128, and then the .129 for the gateway address, which is our router's interface. That's how all traffic needs to exit that network segment, just as a reminder. So that's using equal size subnets within the network, and quite easy to divide up Class C network into smaller portions like that very quickly and easily. And this is the formula for calculating the number of bits that you need. So 2 to the power of n, which is the number of bits borrowed, will give you the number of networks that you can have. Okay, so if you're extending, when you extend from the left to the right, you increase the number of networks. When you're calculating host bits, you're going from the right towards the left. Okay, so by borrowing network, increasing the number of networks, you reduce the number of bits available for the host portion. That's the trade-off. As I've said, -2 for the host calculation, because we can, all zeros is the network address, all ones is the broadcast address. So we lose 2 host addresses in every subnet to those 2 fixed points. So everything in between those options are valid host addresses. And so in this example here, they've borrowed 2 host bits to create 4 subnets, which gives you 00, 01, 10, and 11. And so that means they increment in groups of 64. So 0, 64, 128, 192 are our 4 networks. And there's an example of it subnetting those networks. I won't bore you with going through it again, I've already explained it, so it's just going through there. And you apply those addresses just like you would on any other address space, and you calculate the subnet mask, right, based on our conversion of dotted decimal addresses, just like IP addresses. So remember, the subnet mask is all binary ones to represent the network portion. It always starts from the left-hand side and goes to the right. There is no going the other way, and there's no swapping ones and zeros in the middle of the stream. They have to be consecutive ones to represent networks. Once you start putting zeros in, that's the cutoff at the last point of consecutive ones. And this is just going through various prefixes and creating values. So I'm not going to repeat the same words again on each slide. That's just going through, getting you to calculate from various starting points with different network portions to get you used to it. So you can calculate on the number of hosts that you need to have available in the networks portion. It's exactly the same calculation, but all what we're doing is reserving the number of bits for the host range. So if we need 60 odd hosts in a network, so we need to calculate how many bits we need for 60 hosts. okay, which is 6 bits, because that'll give us 64 hosts minus 2 gives us 62 usable hosts. So we know we would have to reserve 6 host bits so we can borrow a maximum of 2 bits to become new network portions. So in that case, we could divide the original network into 4 segments, each supporting up to 62 hosts. Alright, so it makes no difference if the question is asking you to calculate a number of new networks or a number of new hosts. Or what you've got to do is remember the direction of the bits that you are working with. So host bits start from the right hand side and go to the left, networks from the left and work backwards. So as long as you remember that basic concept, any question, depending on the wording, number of hosts required or number of networks required, it's just the direction of the bits that you're borrowing or reserving. So quite often in designing a network, we'll divide the network into the departments. So each department will have their own segment of the network. So this provides us the ability to apply filtering and so forth, so security policies and all that depending on the department, because human resources, we don't want people accessing records in human resources, but we want human resources to gain support and that from other departments and so forth. So by having the network broken up into these smaller segments, we can apply a policy at the boundary points of these networks and on the direction flow, so we can control who gains access to each department and what that department can have access to on its way out as well. And it becomes quite useful for controlling traffic as we go through. So basically in this example, it's saying we've got a topology diagram. So as a network engineer, you would need to form an addressing scheme based on the number of hosts. So looking around, find the segment with the largest number of hosts on it. So if we remember our, binary breakdown, we have 40 falls between these 2 points. So what we can say is if we divide the network there, that'll give us 2 bits for the network and 6 for the hosts, and that will cater for 40 networks, host devices. Now, are there any others that are above 30? Yes, there is. There's the 32. So I need 2 networks that support 60 hosts. All right, then you come down. There's that one. So 30 hosts. The next breakdown after 30 is 16. So which networks do range between 30 and 17 networks? So these 2. So we need 2 of that will support 30 hosts. And then we have 1 that supports 10. and then we have 1, 2, 3, 4 of that supports our point-to-point links. So we now know from that how to break up the network. So by using the largest portion first, we can now break up the network. So by using our 2 host portions, so in this example we have a /22, and which means we have 10 bits, which falls over the octet boundary. So we need to just reserve our 6 bits, which means 4 bits are available for networking, and 2 to the power of 4. Anyone? No? No feedback in the chat? No. So again, 2, 4, 8, 16, 32, 64, 128. So 16 networks would be created. So we could grab any of these and assign it to the first one. So, alright, so this will become LAN 3 and then LAN 4. And then we could just grab this one and divide it into smaller portions, for example. Alright, so they can, that's a very, very poor example. Okay, we're using cited notation, but they're giving everybody the same portion, which is just the same as classful addressing. Alright, so would that work? Yes, it would, but it's not the most efficient way of doing it. Okay, that's how we would do it in classful addressing. Every network portion of the address space is the same. Alright, it will work, but look here. So we lose 60 host addresses by 4. So we have just wasted 240 hosts under this addressing scheme just on our point-to-point links. Not the most efficient way of doing addressing today. So the labs today are all around doing subnet calculations and applying them to packet tracer, which will tell you whether you've got the addressing correct or not through the scenarios. So as it was highlighted in that last example, we waste a lot of addressing by using the same size host portions across the entire network when we don't need to. So we use variable length subnetting masks now to break it up into smaller portions that only give us the number of hosts that we need for the appropriate network size on each segment. So we can take any network and break it up into smaller parts. Now, the way I was taught to do it is you always break up your broadcast network first. So because your broadcast network, you basically can't be used because it's the broadcast. So if you divide that up into our smaller portions, that's little bit there is our broadcast network. So we can regain all these addresses here to use on point-to-point links. Okay, so you could grab any of these and break it up into smaller portions. It doesn't matter, as long as when you break it up into smaller portions, you do not exceed the original network boundary when you break it up. You can't overlap addresses from one network to another. So basically, we take our original network, doesn't matter where it is, and this tells us our new starting point. So it's /24, and if we need to break it up into smaller portions, like in here, we are doing subnetting for point-to-point links. So we're only leaving 2 host bits. So our new network becomes the /30. So we've borrowed an extra 3 network bits. So our original network is 111, which is 224. And then we start at all zeros via the extension and just start incrementing it up by the new boundary, which is 4. Okay, and we can then select any of those networks to do our point-to-point links efficiently, because we only have the network, first host, last host, and broadcast. So that makes up our 4 addressing space. That one's reserved, that one's reserved, and we're left with our 2 usable hosts. Alright, so plenty of examples and practices for you to go through in this chapter about using this and applying it to the various labs. And from this point on, I will be giving you little exercises to do as far as here's a network diagram or a description of a network, go do the addressing and calculate the address range and start practicing creating those networks in Packet Tracer as we progress through to the final chapter of this module. So I've already talked about the benefits. We get to save wasted host portions between classful and classless. So our addressing uses better proportions on what we're doing. Now, when we look at a network diagram, we need to plan, because now it's got to be hierarchical. So you're looking at a pyramid type structure. Now, the reason we do this is so that when we're up the top in the network, we can summarize routes. So the idea is to take a very general address and then break it up into specific portions, i.e. our subnets, and then break up each of those into various portions as well. And what can then happen in the route summary, which will be in the next series of various bits and pieces, So when we get to those breakout points in each step up the tree, we get to summarize all those addresses. So all these addresses that coincide to the network down here, we can summarize here as all of the addresses in that space. So when we are here, it's one entry in the routing table, not 6 or 7 or 8. So our routing tables become more efficient if we can just break up our addresses like this and make them fall down the branches of each network. So if we just took example there and then broke this one into 4, but we used one of the addresses over here, we can't summarize this branch, because if we put a summary address here, that would include all the sub-networks here. The routing entry for this one would want to come down this path, which is not joined on. So we have to be careful on how we do our addressing, and so just be careful with that. And so by planning ahead, we make the addressing more efficient, and our routing tables, which the smaller the table, the more efficient the lookup process and forwarding of packets through the network becomes. So assigning these addresses to the end devices, again, we would normally use DHCP, which allows us to assign it automatically, and it stops problems occurring. And the same with IPv6, we use the DHCP v6 server and Slack to assign addresses out. What still has to be configured manually is fixed points. So within our fixed points, we need to think about how many servers will be around how many printers, intermediate devices, such as switches that need a manual IP address set, but they need to be part of the same network segment that they are in. So within that, again, following a hierarchical approach, we just reserve a group of addresses for each one. Now, it can be any address range. It doesn't have to follow binary bit portions, because we're not doing that. This is just reserving addresses for use. So basically, we would say in the DHCP server that it can assign addresses between .1 and .229 on the 1.0 network, and then we would manually assign addresses depending on our addressing scheme out to the fixed points. And here's the lovely exercises for you to do regarding those addressing schemes and planning the hosts. So Remember that as a general rule, IPv6, the first 64 bits is our networking space, and our last 64 bits are our general host portions. And most people will use the UE64 method of using the MAC address being split open and having FFFE inserted to create their unique host portion address. So that only leaves us with this subnet ID portion of that 64. So we will have the global routing prefix and then the subnet elements given to us by our service provider. And after that, we get to subnet what's left. Now, depending on the size of the network that we get off our service provider will determine how we subnet. Can you break up into here? We can, but it's not recommended as best practice because we've got so many of them. And just remember, each one is a live network, and we've got 65,000 subnets in each of those networks. So you won't get generally a large address space like that from your service provider. You'll probably get a portion of that as they allocate that to individual enterprises that are within their overall network. Basically, just to sign them off, each network gets their own portion, and you have local link addresses in that. So it's very easy to allocate network addresses under that scheme. And straightforward addressing. Alright, so most of our work will be concentrating on IPv6, and any IPv6 stuff we do will be very simple networking ones. Now, I will be turning the chapter exams and so forth back on after we finish here today, because they basically finish up everything